Hi, my name is Soyun, and I'm a South Korean artist, researcher, and educator based in Den Haag in the Netherlands. I research the relationship between political structures of media technology and the human body. And I look at these subjects through humorous and critical perspectives, choreographing audiovisual devices that challenge the boundaries of cinema. From 2024 to early 2025, I was part of a research group called Moving Media Lab, where practitioners from different artistic fields met to research intersections of technology, dance, and moving image. In this research, I collaborated with the filmmaker Breke Peneke and dancer-choreographer Olympia Kotopoulos on a project called Autonomy of a Fall. This project in a nutshell can be formulated as a question: what happens when a body is captured, categorized, and interpreted by a machine, especially at the moment it loses control? Especially, we were very interested in the threshold between standing and falling, the shades of a fall. During the research, we encountered an AI system called image-based Human Fall Detection, a software that identifies whether a person in an image has fallen or not. We decided to use this tool to conduct a series of experiments with participants from Moving Media Lab. We created an environment where participants were invited to fall, both while being watched by the algorithm and without it. What emerged were remarkably different responses. Each person enacted falling in their own way, revealing the act as something deeply subjective and expressive. This inspired us to amplify that subjectivity, to engage falling as an experimental ground for open discussions. These kind of algorithms are trained to identify the act of falling, often used in an elderly care or security context. And they are built on standardized datasets where movement is labeled binarily, such as either normal or abnormal, safe or dangerous. I argue that these binary classifications, inherently created for machine learning dataset, erase the nuances of how bodies actually move, their hesitation, imbalance, recovery, or play. So in this tutorial, I will demonstrate how to build an alternative dataset for fall detection, one that reclaims the space between falling and dancing. This tutorial is specifically made for a model hosted on GitHub, but it also outlines a general process useful for working with other pre-built machine learning projects. By the end of this session, you will have a small, custom trained model capable of recognizing expressive movements that don't fit neatly in the categories of falling or standing, but rather live in between those states. Looking at wonderfully various movements of the participants, I personally labeled this as dancing, but you are invited to explore what lies in between for you. The goal isn't to make a more efficient fall detector, but it is to understand and query the dataset, to complicate it, and to see what the machine learns when the data itself resists definition. During the Anatomy of a Fall experiment, we recorded participants performing subjective versions of falling. Each person interpreted this act differently, some slowly collapsing, others leaping, sleeping, and hesitating. We used a single static camera, a DSLR on a tripod with consistent lighting and a plain background to focus on the body's motion. Later, I extracted fragments from those recordings, not the movements of impact, but the in-between gestures, the suspension, the almost fall, the recovery. After filming, I decided to manually change the background in Photoshop. This wasn't strictly necessary. Keeping the original background would have worked fine, but I wanted to make sure the dataset wouldn't be influenced by background patterns or textures. By varying the background, the model learns to focus on movement itself rather than associating a specific floor or wall with a certain label. I reclassified these sequences as stands, a simple yet deliberate act of renaming. When you build your own dataset, consider this question: what lies in between falling and standing for you? How do you define what counts as falling? What gestures are missing from this existing dataset? Once you decided on what movement you want to subjectively define, you can simulate this movement over and over in front of a static camera. It's also possible to create a dataset using only one performer, even yourself, by repeating the movements in varied ways, changing speed, direction, posture, and energy. This approach keeps the dataset consistent and easy to manage, though it may limit how well the model generalizes to other bodies or movement styles. If the goal is to make the model more adaptable, adding a few different performers later helps diversify the data. Now that you've extracted frames showing the movement between standing and falling, the next step is to prepare them for training. To make my dataset more diverse and prevent the model from overfitting to one background, I manually adjusted frame dimensions and generated new backgrounds in Photoshop. However, this step is not strictly necessary. You can also use the original frames as they are, depending on your project. Once your images are ready, make sure their file names are clear and consistent using sequential numbering. For example, dancing001 JPEG, dancing002 JPEG. This naming structure is important because the corresponding text label files match the image file names exactly. Then go to the website makesense.ai to create labels for your images. Since we are retraining an existing model, it's useful to first check which labels are already used in the original dataset. In this case, I found 3 labels: fall detected, walking, and sitting. Add these same labels in Make Sense, and then create a new label called dancing, for example. It'll assign it as class 003. Next, manually annotate each image by drawing a bounding box around the body or the area representing movement. Once you've finished labeling all the images, export the annotations in YOLO format. They will be downloaded as text files that correspond to each image. Each text file contains 1 or more lines describing the bounding boxes in YOLO format. Here, 3 corresponds to the class dancing, and the remaining numbers represent normalized coordinates, values between 0 and 1 for the bounding box's center position and size relative to the image dimensions. Now that you have exported all the labels from makesense.ai, let's organize the dataset so that it's already ready for training. First, make a copy of the original dataset folder, the one that came with the model, and give it a new name. This way, you can keep the original file safe while working on your own version. Next, add your new data. Move the images you've just labeled into the corresponding images folder and place the text label files, the ones you exported from MakeSense.ai, into the labels folder. Make sure that the file names match correctly. For example, image001.jpg and image001.txt. Then we will split the dataset into training and validation sets. Usually it's about 80% for training and 20% for validation. You can do this manually or by using a short script that randomly moves files into train and val folders inside both images and labels, if you can program it by yourself. After that, open the configuration file. It's usually called data.yaml or dataset.yaml. Update the paths so that they point to your new dataset and change the names of the classes if needed. For example, you might add your new label like dancing to the list. Finally, we will start training. After setting up the environment, you can open git bash on Windows and use cd command to go into the image-based Human Fall Detection folder. Then activate MicroMamba and type this command to start training. So this command is basically telling YOLO to start training your model. The image 640 part means all images are resized to 640 by 640 pixels. It's a pretty standard size for YOLO. Then there is the batch size, batch 16. That just means the model processes 16 images at once before updating its parameters. 16 is a kind of safe middle ground. It keeps training steady without crashing your GPU. You could make it larger if you got more VRAM, but this works fine for most setups. Epochs 20 means it's going to go through the entire dataset 20 times. That's not much, but it's good if you are just testing things or checking that the training runs smoothly. But for serious results, you probably go higher, maybe 50 or even 100. Data custom data YAML points to our own dataset configuration file. That's where we defined where the images and labels are stored and what each class name means. Wait. YOLO version 5 SPT loads a pre-trained YOLO version 5 model, the small version, so instead of starting from 0, we fine-tune it based on our own images all falling and dancing. And finally, cache just helps things run faster by keeping data in memory during training. So this one line essentially kicks off everything. It connects the dataset, the pre-trained model, and the parameters together, and initiates the process of teaching the model to recognize movement as we have defined it. With my RTX 2060, it took me 2 hours to train. Once it is done, let's test how it runs using your live camera feed. Open git bash again and activate your MicroMamba environment. Use the cd command, navigate to the YOLO v5 folder inside image-based Human Fall Detection. Then run this command. In my case, I used the folder exp9 because that's where my latest training results were saved. The source number may vary depending on your camera input. So if you're not sure which one it is, simply test the numbers from 0 to 9. The conf 0.25 part sets the confidence threshold, meaning the model will only show detections it's at least 25% confident about. A value of 0.25 is a balanced default. Now you can see that every in-between movement before falling was recognized as dancing. The final model doesn't classify a specific gesture, but rather a spectrum of motion, the subtle transitions that happened before the fall. This was intentional. Instead of identifying a single distinct action, the model learns to perceive the ambiguity between collapse and control. However, depending on how you define your categories, you could train it to recognize more clearly defined movements. At this point, you've gained the ability to redefine how a machine interprets movement, not just to detect or label, but to rethink what those labels signify. This can open up new directions for artistic research. So you might want to begin to imagine how this practice could feed into other contexts, a film where the camera sees through a system of classification, or an installation where the algorithm's perception becomes spatial, or a performance where the logic of detection itself becomes choreography. This approach engages machine learning with its structure, its way of seeing, categorizing, and simplifying, as a site of inquiry and inspiration. In this case, the system is to reveal the assumptions, thresholds, and possibilities that shape how meaning is constructed through data.